Hello, welcome to Lesson 12, Open Channel Flow, in the gradually varied flow portion of CE 3372 Water Systems Design. And the purpose of this lesson is to illustrate some of the gradually varied flow principles that we're later going to employ using SWIM. We're going to do a few in Excel ourselves, but that's just to understand what's going on in the machine. So gradually varied flow hydraulics, we're going to discuss the principles, the various resistance equations, the concept of specific energy, supercritical, subcritical, and critical flow, as well as normal flow, which we've already seen. Open channels, as you recall, are conduits whose upper boundary of flow is the liquid surface. Storm sewers and sanitary sewers are typically designed to operate as open channels, and the relevant hydraulic principles are the concepts of friction, gravitational, and pressure forces, all balanced at a particular cross-section. For any given discharge, the flow at the section is described by the flow depth, cross-sectional flow area, elevation, bottom slope, and mean section velocity. These relationships are not necessarily unique, and knowledge of the flow type, subcritical, critical, or supercritical, is relevant and necessary. Go through some definitional sketches here. So our flow depth is the depth of flow at a station or a section measured from the channel bottom. The elevation of the channel bottom is the distance from a reference datum. You'll see in this diagram that the angle is exaggerated, while in essence we're really measuring in the vertical, as shown here with the solid lines. We treat the slopes for the purposes of depth measurements as small enough that we don't get too concerned with that angular deflection shown here. The bottom slope of the channel is typically, the typical nomenclature is S sub 0. The slope of the water surface elevation, which coincides with the hydraulic grade line, I'm calling it S sub WSE for the slope of water surface elevation. And the energy grade line, its slope shown here, the red dashed line, is S sub F, also called the friction slope. Like closed conduits, the various terms are parts of mass, momentum, and energy balances. Unlike closed conduits, the geometry is extremely flow dependent, and the pressure term becomes replaced with flow depth. So an open channel, these are the following analogs to our Bernoulli's equation from earlier. The pressure head is the depth y. The velocity head is v squared over 2g, as before. The elevation head is z, the elevation of the bottom of the channel, and the total head is y plus z plus v squared over 2g. The channel slope, S sub 0, between two sections is typically z1 minus z2 divided by the distance between the two, and it's positive in the down gradient direction. The friction slope is the total head, h1 minus h2 divided by L, also positive in the down gradient with respect to friction slope direction. So uniform flow is flow in the channel where the depth does not vary along the channel. In uniform flow, the slope of the water surface is the same as the slope of the bottom surface is the same as the slope of the energy grade line. We've seen this diagram last time. Uniform flow in this diagram would be the case where the depths y1 and y2 are equal. In that situation, the velocity terms would also be equal, and the friction slope would be the same as the bottom slope. Gradually varied flow, however, that's not the case. The flow depths of the different sections may not be the same. Generally, the change is gradual, moving upstream or downstream. The water surface, as you recall, is the hydraulic grade line. The energy surface is the energy grade line. So in gradually varied flow, we have this situation where at a section we have the flow depth indicated here by Z. We now have a pressure head term indicated by Y and a velocity head term. If we consider just above the channel bottom, so this rose colored bar right there at section 1, and we'll consider this rose colored bar at section 2, those bars represent a property that's called the specific energy of a section. And the specific energy of a cross section is the velocity head plus the pressure head or the flow depth. And in this diagram here, the specific energy at section 1 is V1 squared over 2G plus Y1. The specific energy at section 2 is V2 squared over 2G plus Y2. And we're going to use these definitions of specific energy shortly to develop the gradually varied flow equations, as well as a technique for finding the shape of the water surface. If we make the replacements, we now can rewrite the modified Bernoulli's equation as E1, the specific energy at section 1, plus Z1 minus Z2 is equal to E2 plus the head loss. We can replace that by the bottom slope multiplied by the spacing delta x, and we can replace this term by the friction slope multiplied by the spacing delta x to come up with this expression: E1 plus S0 delta x equals E2 plus S sub f delta x. So that's still our energy equation, we've just changed letters of the alphabet. That energy equation is worth repeating, and it's used to relate flow, geometry, and water surface elevation in gradually varied flow. The left-hand side, which incorporates bottom slope, relates to the right-hand side, which incorporates friction slope. So one can argue that these two terms are balancing gravity's ability to pull water downhill and friction's ability to resist flow. And then those differences are respected by the energy balances E1 and E2. If we rearrange that equation, we can rewrite it in terms of S0 minus S sub f is equal to E2 minus E1 over delta x. And in the limit, as delta x goes to 0, so if we go ahead and take the limit, we come up with this expression that says S0 minus S sub f is equal to dE dx, the first derivative of energy with respect to spatial position, or first derivative of specific energy with respect to spatial position. We can now use the chain gang rule and re-express dE dx as the first derivative of specific energy with respect to depth multiplied by the first derivative of depth with respect to spatial position. And the reason we're going to do that is we now can express dE dy in terms of the channel properties. And it turns out that the specific energy, the first derivative of specific energy with respect to depth, is equal to 1 minus the quantity q squared over GA cubed multiplied by the quantity dA dy. And it turns out that this entire group of terms happens to be equal to a dimensionless number called the Froude number squared. dA dy, if you recall, is going to have something to do with the top width, because if you remember, we integrated an area panel to get the area as a function of depth. We'll get to that shortly. So now we'll make the substitution, and we now have S0 minus S sub f equals 1 minus the Froude number squared dy dx. We'll rearrange this formula, and now we have what's called the gradually varied flow equation. So the variation in water surface depth is equal to S0 minus S sub f over 1 minus the Froude number squared. This S sub f term is determined by discharge in section geometry. The Froude number term is also determined by discharge in section geometry, and this term S sub 0 is simply topographic slope. So the basic equation of gradually varied flow is dy dx equals S0 minus S sub f over 1 minus the Froude number squared, and it relates the slope of the hydraulic grade line to the slope of the energy grade line and the slope of the bottom grade line. This integration is integrated to find the shape of the water surface and ultimately how full a sewer will become. Before getting into the water surface profiles, let's look a little bit of review of critical depth. Specific energy is a function of depth. It's also a function of discharge, and it has a minimum at a location called y sub c, the critical depth. So here's the specific energy equation. Once you pick a discharge, the specific energy versus depth will plot along some curve. And so there'll be a unique curve for each discharge in each channel cross-sectional shape. In this diagram here, the minimum of the specific energy curve occurs at this depth called y critical. If we rotate the curve 90 degrees in a more conventional way of expressing it, energy is plotted on the left-right, depth on the up-down. And what it tells us is this is for some particular value of Q. If we go to, I'm just going to pick that depth arbitrarily. It's telling us that the specific energy, that portion of it is based on flow depth, and this portion is the V squared over 2G. If we go down here, we see that there's very little associated with the flow depth and quite a bit of energy associated with velocity head. And so what these specific energy diagrams do is give us information as to how much of the specific energy is because the water is deep and how much of the specific energy is because of the kinetic component contained in the velocity head. So the minimum depth occurs where the dE dy is equal to 0. That's the necessary and sufficient condition for a minimum. The gradient must vanish. We'd already know that dE dy equals 1 minus q squared over ga cubed dA dy. dA we know is equal to T dy. So dA dy is equal to the top width as a function of y. That will come in handy. And if it has a minimum at y sub c, we're simply going to set dE dy equal to 0. Or if we observe that this component is a Froude number squared, we simply set this Froude number squared equal to 1, and that tells us the value of depth at which critical flow will occur. The top width and area, depth dependent. We've seen this already last lecture. Here's a diagram again illustrating the component that's contained as kinetic energy versus the component that's contained as depth energy. And when the depth is such that the kinetic energy dominates, that's called supercritical flow. And when the depth is large and the kinetic energy component is small, that's called subcritical flow. And the transition point is called critical flow. And the flow regime affects the slope of the energy gradient, which ultimately determines how we're going to integrate the gradually varied flow equation to recover a hydraulic grade line. So finding critical depths, we'll start with a rectangular channel. We already know the depth area and depth top width function. We substitute those functions into the various definitions. In our case, we want critical depth occurs when the Froude number squared equals 1, or when q squared over g b squared y cubed is equal to 1. Solve for critical depth, and we get y subcritical is q squared over gb squared, quantity to the 1/3 power, the cube root of q squared over gb squared. Trapezoidal channel, we will play the same game, although with different depth area functions. Substitute them in. In this case, there's no really elegant closed form solution. Normally you would just do this by trial and error, or you could use the HEC 22 design charts. Either way, you would guess a value of depth, make the computations until you get Froude number equal to 1, and then that would be the case when the flow depth is at critical depth. As an example, here is a trapezoidal channel, 500 cubic feet per second, bottom width of 20 feet, side slope of 1. And The Froude number squared is shown as q squared over g, quantity b plus 2y over m over quantity by plus y squared over m cubed. Substitute in the numerical values, and we will just guess values of y. So we set y equals to 1, Froude number is 18. Too big, in that case that's supercritical. Set y equals 2, Froude number squared is 2.2. Y equals 3, Froude number squared is 0.6. So critical occurs between depths of 2 and 3 feet. Go 2.5, we have Froude number 1.09. I would probably actually quit there, but since we want to be super good, we go to 2.56, we compute a Froude number of 1.01. We would call that close enough, and so the critical flat depth in that particular trapezoidal channel is 2.56 feet. We can do the same with circular cross sections. The only part where it gets kind of wonky is when the pipe gets full, the concept of Froude number kind of goes out the window. But until then, we can have supercritical, subcritical flow in pipes, and it does occur. Depth top width, depth area relationships unchanged from before. We would go ahead and take their ratio to produce the Froude number squared as a function of depth, which is shown here. Remember that alpha is also a function of depth, and rather than directly incorporating it, we would specify alpha, specify y, compute alpha, put alpha into the equation to get Froude number squared. This is a recycled slide, and this is also a recycled slide. And what we're trying to do is ultimately find a water surface profile, because that tells us where the hydraulic grade line will be and whether water will stay in or exit our storm sewer system or go above a certain prescribed depth and flood a home, if you will. So the hydraulic grade line is the integral between two spatial locations of dy dx, the gradually varied flow equation, plus dz dx, the position of the bottom, which is equal to x0 to x1 of s0 minus s sub f over 1 minus the Froude number squared plus dz dx, all integrated with respect to dx. The second part, the dz dx, is pretty easy. We're just going to, we just integrate this part, and then we add on the bottom elevation at each spatial location. But I'm trying to do arithmetic here and make it look like we know how to do math. The channel slopes and profiles affect the direction of that integration, whether we integrate from a downstream control point and move upstream, or integrate from a control point and move downstream. The channel slopes are designated as steep, critical, mild, horizontal, and adverse, depending on the relationship of the normal depth, which is what we get from Manning's equation, and the critical depth. If the normal depth for a channel at a particular flow rate is less than the critical depth, that's called a steep slope. If they're identical, if normal depth and critical depth are roughly the same, that's a critical channel. If the normal depth is larger than critical depth, that's a mild channel. If the bottom slope is 0, that's horizontal. And if the bottom slope is less than 0, in other words, the channel is sloping uphill in the direction of flow, that's called an adverse slope. Then there's three types of profile, types 1, 2, 3. And they're determined based on the relationship of the computed depth and the critical depth. And obviously we don't know the computed depth ahead of time, but we can make pretty reasonable estimates just by studying the channel boundary conditions. But if the computed depth is going to be larger than critical depth and larger than normal depth, that's a type 1 profile, fairly common. If the critical depth is less than the computed depth is less than the normal depth, or the normal depth is less than the computed depth is less than the critical depth, then that's a type 2. And lastly, if the computed depth is less than critical and less than normal, that would be a type 3 profile. Most hydraulic textbooks have sketches and sketches of these things. Here's just a few. Well, here's a mild 1 profile. The critical depth is shown here. The normal depth for the channel is up here, and our profile lies above it. That would be called an M1 profile, and we would integrate from a control point upstream. and you have to assume that flow is going that way. Examples of this is flow coming into a pool above a weir or a dam that's overflowing on the top. The type of curve is called a backwater curve. There's an M2 profile, which would also be integrating upstream, and in this case the water is less than normal and it's accelerating towards critical. M3 is the one difference is it's upstream control, and so the water is going to be less than normal, less than critical, and decelerating towards critical. We would integrate downstream in that case. And so here's our flow direction, and here's our integration direction. We can have the same thing for steep profiles. It's just the shape's a little different. So there's a steep 1, integrate upstream, a steep 2, that would also be integrating upstream, and then a steep 3, we're going to integrate downstream. Okay, there's numerous other examples. Any hydraulics text will have these. Any in the readings will have these flow profiles. And they're used to identify control points to start the integration as well as which direction to integrate. So let's return to our gradually varied flow equation and observe that it actually gives us an algorithm for some simplistic but useful cases. One is called what I call the variable step method, and it's called variable step because this spatial step is what we're going to compute. So the spatial steps are non-uniform, and it only works for prismatic channels. And prismatic means nice geometric cross sections. Rectangles, circles of constant diameter, trapezoids of constant side slope. The algorithm is quite simple. Start from a section with known information, calculate the energy at that section, the friction slope at that section, adjust the depth slightly, calculate the energy at the new section, calculate the associated friction slope at the new section, compute an average friction slope, solve for delta x. Then you move to the next section, which used to be 2, rename it 1, and repeat. So as an example, consider a rectangular channel that's 1 meter wide with 2.5 meters cubed per second, bottom slope of 0.001, Manning's end of 0.025, water flows over a weir at a depth of 2 meters, just upstream of the weir, and we're asked to compute the water surface profile. So here's our starting position, x equals 0, and we know the flow depth is 2 meters. We know the discharge rate, and we know the channel width. We would write our energy depth function to make calculations simple. Because it's a rectangular channel, we actually can do that. And so our specific energy as a function of depth is this equation here. If it's not an easy geometry, there's no advantage to doing this. You actually just calculate the specific energy directly from a known depth. Here's our friction slope function. It's simply Manning's equation rearranged. And we start at our known section, which is section 1. At section 1, we know our spacing and our initial position. Bottom slope is given in the problem statement. We calculate the specific energy with our specific energy function. We calculate the the friction slope. And then we want to move to section 2. So here's section 2. We're going to reduce our depth to 1.8 meters and repeat the calculations. So if we reduce to 1.8 meters, our specific energy is 1.89. Friction slope is shown here. Our bottom slope is here, and that would occur 209.3 meters upstream. And here's where these calculations proceed to produce the 209.3 upstream. We enter into the table and repeat. Now we're going to go from section 2 to section 3. At section 3, we'll specify our depth at 1.6 meters, calculate our specific energy, friction slope at the section, bottom slope is known and constant, and we now calculate the distance between section 2 and 3 is a minus 215.1 meters. So we write minus 215.1, and right there in the table we have 3 points. That's our x position for section 1, x position for section 2, x position for section 3. We have the flow depths of those sections, and then if we actually kept track of the bottom depth, we could add the two and recover what the water surface profile looks like. Here this has been done, so there's a couple steps here, but these depths here have been added to those computed, those specified flow depths, and then the computed distances are shown here. There's another method which will be much more useful in a practical sense, where we fix the spatial step delta x and solve for the energies. In that case, we come up with implicit nonlinear difference equations, and they depend on one another. And for the purpose of this class, we're not going to go through the actual algorithm. It's a little complicated. Nothing y'all can't handle, but there's no point. We'd use a tool such as SWIM or HEC-RAS to handle these calculations. We can also do this for a circular conduit. So the only difference in a circular conduit is how we get the Froude numbers. And let's compute the water surface elevation in a circular pipeline on 0.001 slope, Manning's N of 0.02, discharge of 11 cubic meters a second, diameter 10 meters. Is a big pipe. That's 30 feet across. You can drive cars through that. Downstream control depth is 8 meters. So like before, we would set up a computation sheet. In this case, it's just complicated enough because we have to calculate these angles that you want to do this in a spreadsheet. But we literally apply the same procedure as before, and we calculate the spatial changes as we move upstream, and finally we can plot the results. So let me take a quick foray into those two spreadsheets. So here's the rectangular one. I've done it in a 5-meter wide channel, but otherwise it's the same problem as in the notes. Here's section 1, which is the known section, and I want you to keep your eyes up here as I flip through the cells. So section 1, specified depth of 8 meters, flow width of 5, areas, width times area, calculate righted perimeter, calculate hydraulic radius, calculate the velocity, which is just the discharge divided by the area, calculate specific energy by the usual formula, calculate a friction slope, bottom slope is specified, delta x station are 0, that's our known condition, and then we do our first step. We reduce the depth to 7.8 meters, perform all those calculations, and we discover it's minus 293 meters upstream. Our station is minus 293. Our bottom elevation at that point is 0.293. We add the 7.8 to the 0.293 to get the 8.09 water surface elevation. Move to the next station. Station 3, depth 7.6. All the requisite calculations. New spatial difference is minus 302 meters. We add the minus 302 to the 293 to get a minus 594. Bottom elevation at this location is now 0.595. We add the 7.6 to the 0.595 to get an 8.19 water surface elevation, and we continue. So as we scroll down, we can see the various calculations that are made, and then make it interesting. The whole point of this is to be able to plot it. And so that blue line is the water surface elevation, hydraulic grade line, and the brown line is the bottom elevation. Let's go ahead and fix this. let's call a hydraulic grade line. There. Actually, you'll notice in the graphic that the spacing is changing as we proceed with the calculations. Okay, the other one for circular flow is here. I'm using the same setup as in the problem statement in the notes. Methodology is identical, except now we have the alpha, the angle calculation, uses the various components and starts calculating spatial steps, bottom elevations, and gets water surface elevations. And when we plot it, again, you'll see how the spatial steps are behaving. Okay, well that concludes this video. Our next class meeting we'll do an introduction to SWIM, which is an alternate tool to make these kinds of calculations on our behalf. It's quite a bit more flexible because it's got a nice graphical user interface and we have choices of a lot more geometries. Thank you for your attention and have a great day.